artificial sweeteners that we use for our coffee or tea instead of sugar. We introduced these compounds. They are new to the environment, but we have seen that microbes in wastewater treatment plants are able to degrade those right now. So they evolve. You know, they see new things and they evolve in it and they start to break them down.
Water is the liquid of life. Water is delivered to us where we need it. Turn a faucet, and there is water.
Water is life, as we all know. We need water for drinking. We use it for producing our food, for industry. We use it for our energy. So basically, we need it for everything that we do. Now, the thing is that, you know, the water that we are having, it becomes limited, you know, both in quantity and the quality of the water, because we have climate change effects on water and population growth. And we have the quality of water, which is becoming a problematic thing. And that is related to the chemicals that are emerging in our waters. So these we call chemicals of emerging concern. And these are chemicals that we find more and more in our waters because of population growth. We have more pharmaceuticals in our waters. So when we use our medicine, we go to the bathroom and then it ends up in our water systems. So in the end, we have a lot of pharmaceuticals, agricultural pesticides, industrial materials that all end up in our water streams, and we need to either prevent that they are there or we need to remove them, so clean it up.
They're called forever chemicals.
They're among the most persistent substances known to humankind.
Everything from cookware to cosmetics have left a toxic legacy.
Substances no one wants in their drinking water.
Prevention is one thing that is can be very complicated. We find it hard to prevent the use of, for instance, forever chemicals, PFAS, something that we see that is, you know, a compound that is very persistent in our environment. It's possibly very bad for our health, but we find it hard to ban the use of these chemicals. Same for agriculture, for pesticides. So one thing is prevention and the other thing is then mitigation, right? That we have to remove them. So that's where water treatment comes in. There are various ways to treat water. You can do it with microbes. You can also do it with physical chemical methods. So advanced oxidation, filtration using membranes, sorption processes. And the thing is that all these processes, they take a lot of energy and they produce a lot of waste. We don't really have a sustainable way of getting rid of that yet. So I always advocate for using more biological treatment because it's more sustainable, it uses less energy, and in the end it's more efficient. And biological water treatment has been used for a long time already. We have actually been using it since maybe 1920s or 1930s. Ever since we use biological water treatment, our water quality has improved. In biological water treatment, we use microbes, so tiny microorganisms that eat up all the contaminants in water, and basically all the stuff that we put in our toilets, they convert it to harmless substances.
The water quality, even in national parks, is really not fit for purpose for humans and certainly not for nature.
Where they've been dumping toxic sludge into the river for decades.
For these chemicals that I just mentioned, I am investigating how to make microorganisms eat the pharmaceuticals that are in our systems, the pesticides, plastics, these forever chemicals, the PFAS. I'm looking at how I can get microbes to eat up those compounds. So how to make microbes eat up these chemicals. So what you do is you look in the environment, you're trying to find the microbes there, maybe in places where these compounds are present, then you have more luck. You take microbes from those environments, you go to the lab, and you feed these microbes these chemicals continuously. So you give them all the time pharmaceuticals or plastics or forever chemicals. And then eventually, like also we see in nature, they evolve and they start to grow. And when you have been growing them enough, you can maybe put them back in the environment. That's called bioremediation. Bioremediation has been applied since the 60s to remediate soils, so to clean up soils that are contaminated with hydrocarbons that come from oil and fossil fuels. And we've seen that it has been very successful. We just haven't used this concept in water treatment systems yet, and I think we really have some opportunities there.
Scientists are sharing their research on the microorganisms in the hope that more of the continent can be cleaned up.
The potential of plastic-eating bacteria.
What is preventing rapid adoption of this is we seem to prefer these other methods that I mentioned, so these physical chemical methods like oxidation and membranes, because they are methods that are robust, they're reliable, they give you what you need. Microbes are more difficult to work with, they are less predictable, and we seem to be a little bit afraid of applying those at full scale. But if you look at history, we see that water treatment has improved since we use biological treatment. So we know how to deal with microbes at full scale. And I think we're just, at the beginning of figuring out how to use them for more.